And I choose this very non-technical title on purpose because I thought it would be quite a mixed audience. And it gives you the kind of main ingredients in non-technical terms, but it also is a metaphor for the mood swings that the people doing these models have been going through during the last year or two. And you'll see why as I present the, so to speak, latest results. So if you're a stellar astrophysicist, you would probably prefer a title like AGB stars, dust rings, and spectra. I take the risk of boring you by reminding you what AGB stars actually are. In a nutshell, it's the future of the sun. In somewhat more words, it's evolved low and intermediate mass stars. So stars that start out with somewhere between 1 solar mass and maybe 8 solar masses or so. And by the time they have gone through core hydrogen and core helium burning and burning alternately hydrogen and helium in shells surrounding an inert core, they have reached this part of the HR diagram that we call the asymptotic giant branch. So we're dealing with high luminosities and low temperatures, and this is actually these are actually two very important ingredients in the following talk. The schematic structure of an AGB star could be depicted like this. As I said, in the very interior you have a core that consists of carbon and oxygen, where no nuclear processes are going on. Then surrounding this core you have these alternating burning hydrogen and helium shells. And again, surrounding that, you have a convective stellar envelope, or as some of us like to call it, mantle, to make a difference compared to the certain stellar envelope. And then the star as a whole is pulsating, which means that as it contracts and expands, it creates waves in the very thin outer layers in the stellar atmosphere, which eventually turn into shock waves as they propagate outwards into thinner and thinner material. And these shock waves are very efficient in compressing the gas, and they are also very strong radiative shock waves, so the gas is actually cooling quite quickly too. So in the wake of the shocks you get dense, cool layers at a certain distance from what you might call a stellar photosphere. And in these cool layers, complex molecules and solid particles, in astronomical slang dust, can form. And now comes one of the parameters I mentioned, the luminosity. If we have several thousand to several 10,000 solar luminosities, that is, or may be enough to exert enough radiation pressure on these solid grains to actually drive them away from the stellar surface, and by collisional coupling to the gas actually drive a massive stellar wind. What is typically observed in such stars are winds that are very slow, somewhere in this range, 3 to 30 kilometers per second, and the mass force rates, on the other hand, are very, very high, starting somewhere out probably 10 to the minus 8 solar masses per year, going up to 10 to the minus 4 solar masses per year. So they have a serious impact on the further evolution of the object, but of course also on the observable properties of the individual stars. So these are two good reasons for trying to model this process as realistic as possible. And in order to do this, of course, you use radiation hydro models with a few extra ingredients. The first thing I want to point out is that the radiation field is really complex due to all these molecules in the stellar atmosphere and the dust grains, and on top of everything else, of course, it's variable. So here you see an example from a model actually showing the hydrostatic model in the background and how the spectrum would vary during the pulsation and variations of the star. The second ingredient, of course, is gas dynamics. The keywords here are convection and pulsation. In the type of models we're doing, which are atmosphere and wind models, we have our inner boundary sitting somewhere just below the photosphere, and this is why I write boundary conditions here. So these processes usually enter as variable boundary conditions into the modeling on the inner boundary of the model. The model is a spherical shell that extends either into the outer atmospheric layers, or if there's a wind, probably 20-30 stellar radii away from the wind until the outflow has reached its terminal velocity. Shock waves play an important role in the whole business, as I mentioned before, by compressing the gas. Then we have, so to speak, non-standard ingredient here in the radiation hydro model, and this is dust formation. And thanks to Christiane's many equations, I don't have to go into any details here. The situation for a cool giant is not as bad as for substellar objects, but the basic philosophy is the same, that you describe the dust formation as a non-equilibrium process, and you have to take chemistry into account to some extent. What do I mean by non-equilibrium? Well, the temperature comes into this game because it acts as a threshold, of course. Above a certain temperature, no condensates can exist, or condensates of a specific kind can't exist. So you need to go a certain distance away from the stellar photosphere to form certain types of dust. But the density of the gas determines the efficiency, that is, the rate at which dust can form and grow. The dynamics of the atmosphere, like the shock waves and the pulsation, on the one hand restricts the time available for dust formation, but on the other hand also helps through increasing the density, levitating material above the photosphere. To give you an example of typical numbers here, we're usually talking about temperatures somewhere around 1000 Kelvin, give or take a few hundred Kelvin for various materials. Condensation temperatures, I mean, which puts us at a distance of 2 to 3 stellar radii, where a stellar radius itself is something like 300 solar radii or so. The density of the gas is somewhere in this order of magnitude 10 to the minus 14 gram per cubic centimeter. And if you do some very simple back of the envelope kinetic estimates, you figure out that to grow a submicron grain will take 10 to the 7 seconds. So this is almost a year. And a year is a typical time scale for the pulsation, for instance, of these stars. And so the conclusion is the grain growth time is comparable to pulsation period, and this is why you need to do all this non-equilibrium time-dependent dust formation. Well, this bit is not new, so to speak. I'm showing you here some models that we have done a few years ago for winds of carbon stars, showing the variations of gas velocity, density, temperature, and dust's degree of condensation as a function of distance here. And what the basic step forward here was that these models combine frequency-dependent radiative transfer and non-equilibrium dust formation, and they are realistic enough to actually predict spectra that look like real stellar spectra. Of course, what we can do right now is, for instance, what we're doing is 64 frequency bins, so to speak, for the radiative transfer and so on. So they're not perfect, but at least they're relatively close to reality. Once we have the spectra, of course, we can, the structures, of course, we can take snapshots, calculate all kinds of observable properties, and I'll show you one particular example here. rotation vibration lines of carbon monoxide. And if you look at different modes, fundamental first overtone, second overtone, for instance, they are formed in different parts of the wind or the dust formation zone or the pulsating atmosphere, and they show very different Doppler profiles. The green curves are without taking the velocities into account. So you get P-Cygni profiles in the outflow, and you get line splitting during certain phases in this pulsating part. Whenever the shock wave is running through the line formation region, you get both infalling and outflowing material in the same line, so to speak. And these things can be compared to observations, and they fit quite nicely. I don't want to go into details here, actually. So these are observational radial velocity curves. These are computed ones here. Okay. Another aspect is the chemistry of the atmosphere. What I have shown you so far are models where there's more carbon than oxygen, carbon stars, and where the dust that is forming is mainly amorphous carbon. And as I just mentioned, these models, they seem to work quite well. We think that we kind of understand how the mass loss works, and we have reasonably realistic dynamical atmospheres. The situation from stars where there's less carbon than oxygen, which is, so to speak, the normal case, is a lot more tricky, because for one thing, the dust formation itself is a lot more complicated. So this is where people started out basically doing detailed models for this case. So here you expect silicate grains to form, and it is only very recent that models have reached kind of a comparable level to the carbon-rich models. So there are lots of question marks left, but there was one kind of interesting result that we didn't really anticipate. Two groups independently, Peter Wojtke and our group, started implementing such frequency-dependent models for N-type stars with non-equilibrium dust formation, and it turned out that the opacities you will get from the dust will not be sufficient to drive winds. The reason being that the grain temperatures, which are dominated by radiative effects, will force the grains to have a low iron content, which in turn will force a very low opacity. I can just quickly flash here a diagram showing an, let's say, opacity-like quantity here. So if you could manage to get ironing, you could get kind of reasonable opacities here in this range around 1 micron or a few micron, where you have most of the flux of the star. If you can't, then you're down to the yellow curve, so you're several orders of magnitude lower. Why is that? You can make very simple estimates for grain temperatures by assuming radiative equilibrium, assuming a Planckian radiation field, and a geometrical dilution as you go away from the star. And then you just approximate the dust opacity by a power law in this region where you have the maximum of the flux. And then you say that the condensation radius is roughly where this grain temperature that you get from this procedure is equal to the condensation temperature of the material. If you do these assumptions, the whole thing gets so simple that you get a very simple formula here for the condensation radius in units of the stellar radius as a function of condensation temperature and stellar surface temperature, and the exponent of the power law for the opacity here. And if you plot this as a diagram as a function of this exponent of the power law, then it looks roughly like this. If you look at the case of amorphous carbon, then for a star that has typically 3000 or so Kelvin, the condensation temperature will be somewhere around 1500 Kelvin, so this ratio of the temperatures is about 1/2. And then you plot it as a function of p here, and you get this curve. And if you pick the appropriate exponent here, you get a condensation radius of around 3 stellar radii, which fits very nice with detailed models, actually. If you take silicates, they condense at lower temperatures, more around 1,000 Kelvin, so this ratio is more like a third than 1/2. This curve gets a lot steeper, and now the exponent in the power law depends very much on how much iron you have in the grains. So if you have no iron in the grains, for instance, olivine grains here, then you end up somewhere down here, so actually at a very similar radius, but then the opacity is very low. The grain opacity is very low. If you include half magnesium, half iron, then the opacity is somewhat higher, but the grains will not be able to form anywhere close to the stellar surface. So this is what I mean by the radiative effects force low iron abundances, because out there the densities are simply too low to form grains. Why wasn't this problem spotted earlier? Well, if you do gray models, like people did before, all models end up here with a power law index of 0. And then you're always in this kind of nice range. So what we suggested recently was, we got so desperate that we said, well, there must be a way around this problem. What if, and I want to really emphasize it, what if the CO molecule is partially destroyed, for instance, by shock waves, and in that way some of the carbon, which is less abundant than oxygen, is freed up and available for dust formation. So we made a model where we had this as an input parameter, the free fraction, so to speak, of carbon, and let silicates and carbon form simultaneously. So in this plot, I'm really sorry about the quality here. You have silicates on the left and carbon on the right, and the only message I really want you to see here is that they basically form at the same spot. And the actual driving of the wind would be done by this fraction of carbon, so to speak. The neat thing here is that actually both things can form simultaneously, because if you would go and drive the wind with an arbitrary force, there would be no guarantee that you could get dust forming, because if you start accelerating the material too early, the densities go down too fast, you just don't have time to form grains. If you don't manage to accelerate the material, then you might also end up without grains. So this is a very recent letter that I wrote together with a colleague from Copenhagen. And of course this is a hypothesis, so this needs testing, but one of the reasons why we got so desperate about the problem that we actually wanted to break this dogma, so to speak, that the underabundant element is completely found in CO, was that actually a remark that an observer, Hans Olofsson, actually, by the way, made, that you can't do this. You can't say silicates can't drive winds, because we know that the winds of oxygen-rich stars look so much like the winds of carbon-rich stars, and if they're driven by a completely different mechanism, how do you explain this? So that would be the neat part, if this scenario really works, that there's a natural explanation why both types of wind look the same, and also naturally, and this is a really interesting coincidence, you could have conditions where silicates can actually form in a wind that is driven by another force. Yeah, no, I think I want to leave it at that. You can always ask if you want to hear more details. So summing up this bit, the role of grains in AGB winds, we think for carbon stars, we are home safe, pulsation hence dust-driven winds seem to work very nicely. We have good agreement with of detailed models with observations. For the opposite case, the better the models get, the more detailed the models get, the worse the situation gets, and we're at the point where we are not even sure if it is actually dust that is driving the winds. Now, since this meeting is called New Trends, I want to show another trend. The models I've been showing you so far, they are very detailed, but they assume spherical symmetry. The reason being, as has been mentioned by many people before, that it's very hard to combine detailed microphysics and 3D simulations, because those things eat a lot of time and you need to compromise. So what we have been trying to do in parallel, and this is work that is done together with Bernd Freitag, who is also here, of course, is to look at what would convection, what effect would convection have on all these processes? Because, as I said, our boundary usually lies somewhere here. We've done some 3D star-in-a-box models of such giant stars. This picture does actually not show a time sequence. It shows what you might call tomography. So this is a slice through the center of the box. This is somewhat off-center, and this is even further off-center, to give you an impression of the 3D structures. And the left column is density, the middle column is temperature, and the right column is dust. And the star, if you can still kind of define a star here, is roughly this size, where you have this slight density inversion. I'm not sure you can see it actually in the projection. And what is happening is that convection cells are so huge in these objects that you have only a few on the surface of the object. So in principle what you get is shock waves that look very much like parts of spherical shocks. So locally speaking, there is very little difference between a spherical model and this kind of model. And what you also see nicely here is that this non-equilibrium dust formation is reflected in the patterns around the star. Dark here means that there's no dust, so of course there's a hole in the middle where the material is too hot. But here, for instance, where this shock front is located directly behind the shock front, you have dense, cool gas, and here dust forms quite efficiently. So this looks like a small sector cut out of a spherical model, if you want. Well, there's a lot more work left here to do. These models are, of course, gray, and they, as you can see, don't reach very far out. And this is, of course, a computational problem. So what we have tried to do is combine these detailed 3D models of the star with 1D wind models by constructing a boundary condition from the 3D model that simulates the global oscillations of the star and put it as an inner boundary condition into the 1D models. And this would result in something like the velocity at the inner boundary looking like this, and the actual sequence is this length, and then we've just repeated it over and over. And we see that even though these variations are very unlike what we usually put into the 1D models, the outcome is quite comparable. Not actually the real temporal pattern that you get in the wind velocity or mass loss rate, but if you do averages, then you get very similar answers, even if you use a different shape, so to speak, of this function that you put in here for simulating the pulsations. Usually one puts in a sine curve, and the crucial parameter here is the maximum velocity. Actually not the average velocity, but really the maximum velocity. So if you put in a sine curve with this same amplitude, you would get a very similar mean outflow velocity and mass loss rate. So I just want to summarize the situation of wind models here with this one slide, which I think is pretty self-explanatory. sea stars have basically reached the stage where we can really apply them to astrophysical questions, and stars are still lagging behind, not the least due to this driving issue of the winds. And 3D models are catching up, but are no replacement yet.
Thanks for some questions. Vincent?
On the model where you show these three sections, how do you treat gravity?
Can I... Where's Bernd?
Yeah. It's a one solar mass star, so it's one solar mass, 1 over our potential, and the very center of the star is smooth, because I don't want to have the white wall in the center. But gravity is constant at the time.
So there's no self-gravity in the atmosphere?
The atmosphere, the outer atmosphere has essentially no mass, and even the outer layer, that's 5 or 3% of the star. So it's very much distorted, but it would shift the center of mass just very little bit. That might be an issue if the simulation become very good. You have to put that in. And there are so many other issues. The dust is not driven out, so I would not put that time in the list. But it's noted, but I think it's a small effect, because the outer layers that are highly deformed have so little mass. 2% of the total.
Mm-hmm. My next question, of course, could I please direct that to this speaker also?
Yeah.
If you don't mind. So do you have to use a fixed grid then, or do you use AMR to refine things towards the central object, or what do you do?
No, so the box is a cube, and the small cells are also cube. And
what's the size of that cube compared with your sun inside? You have a central object, you just said.
No, you see the star has, it's 170 cube cells. So the central object has then 50, 70, 100 cells, depending on the space across. Not more. It's very, badly resolved. Most of the time spent in the radiation transport all over and over again.
This sequence, which is about, I think, 10 years of stellar time, or less than 10 years of stellar time, took about 1 year to compute.
The entire model. So refined are the 1D models. There, actually, AMR if you want. The 3D model can't do it.
Yeah, I was wondering about those big convection cells, which are the major argument that there's good agreement with 1D. If you have a central cell where the convection is coming out, so to say, all the energy and all the boundary conditions are defined, and you have a coarse resolution, having just a linear grid, could it be that if you refine that the convection cells get smaller?
Yeah.
I tried this very same thing with different resolutions with a supergiant, which has a higher mass, so has slightly smaller cells relative to the radius from the outside. And you still get, whatever I could afford, it's not that much, 315 cubes, that's my biggest model. And what happens is this large cell gets substructures, so you consider them as continents, they get a very rugged coast and holes in between. But if you sort of unfocus, you get still a very few cells on the surface, and just a complex pattern on top of it. And you don't get, it doesn't shrink the representatives. We tried this for the sun with other models, so we can afford pretty coarse grid and still pretty good. We just get very smooth cells.
Maybe I can put in a technical remark here, Jürgen. I've once experimented with the difference of what happens when you put the center of gravity in the geometric center of a cell, or in the corner of 4, or 16 in this particular case. And that's a reasonably good test. That's the effect that you mentioned.
So I'm wondering, is this star still pulsating, or is all the motion we see convection?
No, it's pulsating in the sense that if you start tracking where's the mass, that there are global pulsations, and this is what you saw on this curve that is put into the 1D wind model. So there is a pulsation in that sense. The volume taken up by a given amount of mass is changing.
But in principle, pulsation and convection are sort of linked.
Indistinguishable, basically, I would say.
Just a very naive question. I have problems to identify a star in this.
Exactly.
Where is it?
Here, roughly, where you have this inversion here in the. Sorry, I didn't say that's the density. Oh, yeah, it says. Okay.
It's a cross section through the star. Right?
Exactly, through the center of the box. And the action with the dust starts somewhere out here. I can show you the dust movie, for instance. But at that point, it's only the shock waves that are relevant. It's not, so to speak, the convection cells anymore. So this is what the corresponding nasty dust cloud looks like.
Next speaker. Could the next speaker please come forward so we can set it up? There was one last question, I think. Yes, Christian.
I was wondering what happens if you include one-dimensional radiative transfer effects. So if you have this collective cloud coming up and you completely activate it, if I remember how
Glad to see you.
Yes. I think it's quite easy to have radiative transfer.
Sorry, if you have. What I didn't mention,
Repeat the question.
the question, okay. The question was, what would happen if you put, what's it again, one-dimensional, no, multi-dimensional radiative transfer in, because you would get, are you talking about the forces now or about the energies? Yeah, exactly. So, I mean, there is radiative transfer in here. What is not in here is radiative pressure on the dust.
What kind of radiative transfer is in these actual models?
Just three-dimensional, short characteristic,
But not on the...
not the pressure, not the force. The force on the dust is not taken into account. But the radiative transfer is there.
No, that's because this is so large. If I add this, the transfer goes down to sort of zero. Oh, second. And it's lost. And that's what we'll do.
Okay, interference. I'm learning trivial physics. Good.
But we'll tell you when he's integrated.
Okay.
The last speaker of today is Rashid Chunyayev. We're very happy that he can be here, and he'll be talking about integral, the X-ray sky, I guess.
Yes, this is a real title. We are finishing with Nailin Adamov from Landau Institute, new paper about the boundary layer, spreading layer on the surface of neutron star, where we have a lot of different ideas about radiative high dynamics, but no numerics. Unfortunately, Naim, unexpectedly for me, decided to go for 3 months to Japan, and paper was interrupted several days after you wrote me first time. Therefore, thinking a little more, I decided that you know so much more than I in the radiating dynamics, therefore I would speak about another exciting things. This is science coming now from integral spacecraft. It's really exciting for all people who are working in the with X-ray binaries or galactic nuclei, because several things came which were absolutely unexpected. And I will try to share my excitement with you. Most interesting for me now, I'm very interested and I'm trying to work with students on the problem of escape of positrons from supernovae explosions. And this is becoming extremely interesting problem for me, and it is very, very difficult to understand even how to solve this problem. May I tell you first, there are 2 other spacecraft which are measuring today the sky in hard X-rays. This is Swift and Suzanne. Never in history there were simultaneously 3 spacecraft working in the hard X-rays. Now we have this, and there are beautiful results of Swift in addition to gamma ray burst afterglows, but I have no time even to mention in every place. I wish to concentrate on science. Excuse me if I will not quote all other groups which are doing similar things. First, we were in a very privileged situation because Russia gave Proton for the launch of Integral, and in return we got 25% share of observing time. It's a lot, and it permitted us, I am writing here the topics which I wish to describe you, but I am completely certain that if I will describe half of it, it will be great achievement. First, I wish to speak about the spectrum of the positron-electron annihilation line from central part of our galaxy. And it's a beautiful result. The result which is very important for me, now several spacecraft confirmed the central black hole of our galaxy was million times brighter in X-rays 400 years ago. You know, maybe a week ago, or several weeks ago, there was unbelievably bright flare in X-rays and in infrared from the galactic center. But this is increasing luminosity from solar luminosity 3 times for 40 minutes. You understand this? It is very bright, it's strong. Here I'm speaking about factor at least 1 million. And this was 400 years ago, in the times of Boris Godunov and for I don't know which town in Sweden. This was the case when our galaxy was, when our center of our galaxy was low luminosity AGN. And it's very interesting. Second, I wish to speak about discovery of the family of heavily obscured local AGNs. Many new AGNs are detected by a with integral just near close to our nose. At the distance at redshift 0.01, 0.03, 0.05. You know that majority of people, Chandra, is observing AGNs at redshift 2, 3, 6. And I'm speaking about hundreds. But for Chandra, which has a field of view of the order of, good field of view is 20 arcminutes or 15 arcminutes. For Chandra, it's very difficult to cover whole sky. It should walk of the order of several tens of thousands years to cover whole sky. Integral is very unsensitive, but has huge field of view. Therefore, it covers whole sky. And we have now first sample of the local AGNs, just uniform sample. And the last, if I will, 2 last things which I will have time. There is great discovery made by, mainly by Misha Revnitsov in our group, who for 30 years people were not understanding what is the emission, diffuse emission from the galactic ridge. Now it seems that we know As in Russia, we are usually telling 99%, but maybe not. If you understand me, we know that this is a contribution of stars and it's not hot gas. I will describe this, and then I will tell you how we are measuring X-ray background using occultation by us. Maybe, if I will have time. This integral spacecraft, two devices are excellent. This device is giving the best images from 20 to 100 keV. Excellent device. We all dreamed that it will be working up to 1 MeV, but thanks to these people who did it, it's very good from 20 to 100. And another device, this device, it's absolutely great, just absolutely great. These are cooled germanium detectors which have very good spectral resolution. And what are the results? Main result is the 511 keV line from galactic center. It has long history how people detected it. I have no time to describe. These were balloons, American balloons, several spacecraft. But this is a spectrum obtained by integral. And it's unbelievable. Because look, we measure the width of the line with very, very high precision. And line is more broad than the resolution of the instrument. Therefore, width is measured. Second, everybody who was student in good school, he had course of quantum electrodynamics. When I was student, for me, it was necessary every day to put, the spur, and it was very difficult life, but I remember how positron is annihilating very well, and I am amused that we see both 2-photon annihilation and 3-photon annihilation continuous. For people who do not remember this, I will show that when positron is forming atom like positronium atom, but instead of proton, there is positron and electron. Then, if spins are directed in the same direction, it's forbidden to decay to 2 photons, just due to the conservation of angular momentum. Only 3 photons are permitted, and then this 3 gamma, it is continuum. It's not 2 photons. In the case of spins are directed in different direction, we know this is the same mechanism as 21 centimeter line of hydrogen. But when they annihilate, they are giving 511 keV photons. Here they are producing 2 photons with equal energy. I would not tell you, but just statistical weights are such that in order positronium should go 3/4 of cases, and 1/4 of cases is in parapositronium giving narrow line. And this is what we see. I will pretend we see continuum 3-photon decay, and we see narrow line. Immediately for you, I will tell that flux is huge, just huge. Where in our galaxy, in its central part, somewhere in 6 degrees, around galactic center, 2 times 10⁻43 annihilations per second occur. And we don't know how many positrons are forming positronium beams and go out from our galaxy. All our estimates, many other people estimated, it's practically impossible to stop in the galaxy positron with the energy higher than 2-3 MeV. All radioactive processes are giving us positrons with energy several hundreds of keV. It's possible to stop them. But I am very proud. First million seconds which we used, which were roughly 2 million seconds in the direction of galactic center, permitted us to measure the center of gravity of the line in the center of galaxy. And it is the same what we know in the lab with precision 10 times 10⁻⁵. Today, this precision is 3 or 4 times better because we have 15 million seconds in the direction of galactic center. We can measure how our galaxy rotating. We can measure how Earth is rotating around Sun. Just looking to this line, how center of gravity is changing during every half a year. But nobody needs this, you understand this. But what is much more important, I'm doing subtitle. Oh, Okay, you have with me a lot of work as chairman. I see this. Thank you. I will not tell you about all mechanisms, how positrons are decelerating, the reionization, excitation of atoms, interstellar atom Coulomb losses, and what is important, that very important process is charge exchange, when positrons are already very cool. And all this we can compute, we can do Monte Carlo, we know how it occurs. Most important, that it's impossible to stop if energy is high, higher than several milli. I will tell you immediately that we also are observing aluminum line, this radioactive aluminum, but this line also produces decay of this radioactive aluminum, also is producing very big positronium components. I can tell you that aluminum has completely different distribution in the galaxy. It is in the repeating distribution of bright stars, and it's in the plane of the galaxy, and other part is coming directly from the center of the galaxy. But what is absolutely great, we can prove that all this narrow line is produced by interstellar matter with temperature 8,000 Kelvin, plus minus 10%, and degree of ionization in this matter is 0.1. And we are getting this from our simulations and comparison with the spectrum. And if you go to classical paper of McKee and Stryker about 3 phases in the interstellar gas, this is one of the phases which is well known. And it occupies a rather big part of the plane of the galaxy, but it's absent above, and it's interesting. And main mass of the galactic gas is in the molecular and H1 clouds. They do not contribute. If gas will annihilate, if positrons would annihilate there, line will be broader. If temperature will be higher, line will be broader. And we have practically minimum under these circumstances. Yes. Our dream now, everybody is thinking what is the source of these positrons. At least 2 times 10 power 43 positrons per second. Cold positrons. So with energy less than 2 MeV. Only one process can produce these positrons, which is normal, which we understand. This is the nuclear decay of this chain, cobalt to iron 56, and here we are getting positron line. Integral, our dream now, that integral will survive until new supernova will appear not very far. Integral will be able to give excellent science if supernova 1A will appear at the distance less than 8 megaparsec. And if SN2 will appear more close to us to 100 kiloparsec, no chance. But this is really very, very interesting. And this is our dream, because if we will find this, we will get very interesting results. And these are measurements of SN87A, you see here, and this is the spectrum which was observed from Russian space station Mir, Quant. We have several devices, and we obtained this spectrum from 20 keV to detected it to 200 keV. This spectrum was absolutely unusual. Nobody never seen such spectrum, because there were no photons below 20 keV. Everything was absorbed. And spectrum was very, very hot. And I remember how we got interpretation of this spectrum with Sergei Grebenev, just comparing with Monte Carlo decay. This is emission in the decay of the different lines from the cobalt 56 decay. And these lines with energy 847 keV, 1247, 1260 keV, they have many scatterings inside optically thick envelope. And during each scattering, you have recoil effect, you know this Compton effect, and you are moving in frequency after having 100 scattering to very low energy, and here iron and cobalt are absorbing photons and do not permit them to go down. Here nothing, it's upper limit, no photons in standard band. And this was observed, and this is predicted. We see this. Now if there will be a cell 1A at 5 megaparsec, look to the spectrum in 20, 60, 160 days. Then we will see, already on the 20th day, we will see bright lights in the spectrum. And this is 511 keV. It should be bright. It is annihilation of positrons. And great question, what percentage of these positrons will escape from supernova? I can tell you that we need of the order of 5%. All my estimates show no chance to get even 0.5%. Because photons are coming to us optical depth, especially here. Optical depth is 100. How these positrons can go if their annihilation cross-section is comparable, you understand, in the beginning, and they cannot go straightly. Photons are go straight, and these positrons, there is magnetic field and so on, they cannot. But there are beautiful things. Supernova, in the bright phase, has luminosity of the order of 10 power 37 ergs per second, 10 power 36 ergs per second. And with this luminosity, object is super Eddington for positronium atom. Luminosity is so because positronium atom is very light, and therefore there is unbelievable light pressure, which also can organize some motion. There are many beautiful things in this problem, and we are very interested, because people are discussing special types of the dark matter, which can also produce this in the central part of the galaxy. But maybe these are just multiple. Oh, I have begun to raise too much. Okay, the same story. You have a lot of work with this. Yes, thank you.
We can do without the mic.
Do you hear me or not?
Yeah.
Okay. Yes. And I'm really excited, and I will speak now about time when center of our galaxy was brighter many times. And positrons, to escape from the galactic center, they need at least 300 years to go out of the galaxy. They're hot, they go out, they're diffusing. They wish to go to much bigger volume. And characteristic diffusion time is 700,000 years before they will annihilate. They're annihilated very rapidly when they decelerate. And deceleration is very, very long. And here is the following. If there was quasar or AGN on the place of our galaxy, again we had for positrons 100 times super Eddington luminosity. And what was occurring with these positrons and positronium atoms, how they were moving, it's very interesting problem. Maybe not fully dynamical, but very interesting. Let us speak now about the central part of our galaxy. This is 3-day averaging of observation of the galactic center. And you see for many, 10 million seconds. And you see this is well-known black hole, we know Einstein source, very bright, this is the H31 flower. There are many sources. But these bright sources are contributing so much that the background of the whole region is changing. And this blinking is connected with the change of the intensity of the brightest sources. But we are working under these circumstances, and if we just integrate it, this is a picture. Our central black hole, 3 million solar masses, is 4 orders of magnitude bigger than this 10 solar mass black hole. You see, nothing from here for integral, and this object is unbelievably bright. Very, very interesting how to make our black hole so silent. But everybody knows this. We were observing everything around, a lot of data. And the most interesting data came from giant cloud, molecular cloud, Sagittarius B2, which is situated 300 years from light travel time from Sagittarius A star. And what was most interesting, this source is only molecular cloud in our galaxy, which emits a lot of hard X-rays. And this was great problem why it emits hard X-rays. Many years ago, when Markevich and Pawlinsky were still students, now Pawlinsky is deputy director in Moscow Space Research Institute for Science, and Markevich is responsible for all calibration of Chandra telescope. We were thinking how it is possible to detect if Sagittarius A star was much brighter before. And we proposed the following model. Let us consider the Sagittarius A star gave us flare of X-rays. What will be afterwards? Then this is geometrical position of all points from which signal to us is coming in the same time. And if here is molecular cloud, there will be scattering of X-rays and they will come to us. And all clouds which are on the same paraboloid will be shining in the same moment. It's easy. You see here how it's possible to make archaeology. But there is beautiful physics, and this physics is following. There is Compton scattering, therefore some spectrum will be just reflected. But then there is K-alpha line, iron K-alpha line fluorescence. Iron, neutral iron, will absorb X-rays, and then it will give 6.4 kV line. This was our prediction. There should be strong K-alpha line. And then we propose that there should be very strong absorption at low energy X-rays. There is a lot of battles with Japanese scientists and with others that they see K-alpha line and not helium like iron. Now, detectors are much better. We know this K-alpha. Everybody agrees. And this is the spectrum which we have. Integral, RP, and this is ASCA, Japanese ASCA. No emission at low energies, huge absorption, very bright K-alpha line, iron line, and X-ray scattering may be here already, Klein-Mishina formula, decreased beginning. Therefore, it's very, very interesting. This is the spectrum of our AGN, reflected spectrum today by Magellanic Cloud. And we are very happy with this. Equivalent width of this line is 2 keV. Normally in X-ray binaries, this much less than 100 keV or even 15 electron volts. And here it is 2 keV, it's so powerful. It's unbelievable. I will show you our dream. And from the beginning, we were telling that when people will observe it, the brightest point will be moving. And for 7 years, nobody was able to detect it. Now, 2 spacecraft reported that the brightness of Sagittarius B cloud is moving from this direction to this direction. Chandra detected this and then Suzaku. And they see, they have now 4 points here, how the brightness is moving. Bright spot. This front of illumination is moving, and we see how that paraboloid is moving, and we can prove that the width of this paraboloid, the duration of flare, was less than these 10 years of observations. It's of the order of year or 2, maybe. There was food, everything. With black holes, everything is simple. There was food and black hole was bright. Okay, let's go further. This is, I told you that the spectrum of our galactic center was very, very, very high. This is the new FU, and a lot of energy was going at energies of the order of 100 keV. And this is great problem for us now. Why it is great problem? Because we are observing many local AGNs. For example, this is Sagittarius A star, and in 1 degree from it, we discovered long ago the bright Cthulhu galaxy. Nobody was able to detect it because it's so populated region, but we discovered X-ray source, and when people measured the spectrum of this binary, it was typical Cthulhu galaxy. Luminosity is 10 power 44 ergs per second. Our galactic center has luminosity in X-rays 10 to the power 33 X per second. Just two twin black holes, 11 orders of magnitude difference in the luminosity. And this is a spectrum. Absorption at low energies and huge flux up to 150 keV. Spectrum has no decay. Many these objects are very hot. I thought before, I know now that it's not completely correct, but it's nice to speak that radiation spectra of accretion black hole, accreting black holes depend only on their mass, accretion rate, and spin, plus obscuration. And you see here, X-ray binary, which is very deep in X-rays, and this is AGN. And you see spectrum here, and this one is a hot state and soft state. I will not describe this thing, everybody knows. Okay, I will fulfill only 20% of my program, it's okay. And you see the discovery integral increased twice amount of high mass X-ray binaries in our galaxy. Twice, it's a huge factor. And you see objects which integral detected. No one photon in Chandra at XMM data up to 10 keV. And maximum is around 20 keV. Everything is absorbed around. It's like accreting star, neutron star in cocoon. Nothing is going out. And there are many such objects which are becoming bright for 3 days, for weeks, for months, then disappear and then appear again. It's absolutely beautiful. This is the same as quantum 6 Seyfert galaxies, but even better. And there are many dozens of such objects in our galaxy. Great problem for us is the X-ray background. Because X-ray background has this spectrum, and you see, now we just measure this spectrum again, there is very strong fall after 20-30 keV. Maximum is at 20-30 keV. How it's possible if it is coming? We all believe that it's coming from the AGNs. And many AGNs which we are observing are bright up to 100 keV. Or they are at very high redshift and redshifted, or some other, there is another family of those. Then we are working on this now. We have hundreds of local AGNs. We measured this integral. We are studying their spectrum, and we dream to get something similar to the background of what is the initial spectrum. There are two ways to measure spectrum of the sources. One is to observe with XMM Newton quasar at redshift 6.3, most distant quasar. XMM practically cannot observe it. Even 6 multiplied to 7 will be 40 keV. Here we can measure black hole spectrum up to 100 keV. This is unique. And we can measure it, and we are measuring hundreds of objects. Yes, this is how many objects we are discovering. Very bright objects, 6 Seyferts, 3 Seyferts 1, and 4 identified, which nobody knew before, and nobody knew what is the optics. When you look to them with Chandra, when I showed this to Harvey Tannenbaum, Harvey told me, write me letter and tell me how much seconds you need for this object. I told 700 seconds with Chandra. He told me, Rashid, just to go to point to your object, we need 2,000 seconds. Take 2,000 at least. This was his advice. But look, this is the integral points, and this Chandra. From 3 keV to 10 keV, flux is dropping. 1, 2, 3, 4 orders of magnitude. Unbelievable absorption. And there are many such objects. And nobody was detecting them before. They are absent in all local surveys. And we are detecting them. Yes. This is how we were observing the spectrum, properties of the spectrum of X-ray background. Yes, and we are now studying the albedo of Sun, Earth, and Moon. And why we are so interested in Moon? Look, please, everybody heard about salt gamma ray repeater. Source appeared in our galaxy, and this source was brighter than quasar during 0.8 seconds. Just normal neutron star had luminosity 10 to the power 47 per second. And Mazets had two spacecraft. One spacecraft, American Wind, in interplanetary space, and another spacecraft here, Russian spacecraft, very small, and this spacecraft was hidden from the repeater because it was screened by the Earth. And this signal came to the moon, scattered from the moon, and he detected scattered signal. And what was most interesting in the data of Mazets, this unique data, 1 second. It's here, I think. No, even not here. I forgot it. But I will tell you, this device had so high flux that photons were coming 10,000 times more often than characteristic resolving time of his detector and electronics. And the detector stopped to work on the American spacecraft Wind, Russian detector, and all detectors in the world stopped to work when luminosity of the source was higher than 10 power 43 ergs per second. But using this reflected from moon signal, Mazets found the total luminosity was 10 power 47. And there was Japanese device of this dimension. Nobody got from it any X-ray source. It also measured this flux because it was so small and tiny, therefore they were able to estimate, and this is neutron star, which produced 10 power 47 ergs per second. How many Eddingtons? 10 power 9 Eddington luminosities. And beautiful thing now, the last, I will very rapidly tell about this. Thank you for chairman. To chairman, this our galaxy. You see here very bright source. These are XP data. Michael Nitzer took out all these bright source, picked them out, and he found how the X-ray luminosity is distributed here. And this X-ray luminosity was exactly distributed as Kobe signal in infrared. And in infrared, these are just old stars, old stellar population of our galaxy. Absolutely the same, full proportionality. Kobe Dirbe, 3.5 micron, and 3 to 20 TeV map. It was great result, and Sazonov proposed immediately. He found luminosity 210 TeV. We know what is the mass of the galaxy from infrared data, and we found that every solar mass in our galaxy is producing 3.5 times 10 power 27 ergs per second per solar mass. Everywhere. And what is it? Let us think what are the sources. Marangin-Fanov did even more unbelievable thing. This is the emission of our galaxy in 6.7 TeV line. It's again exactly the same. Lines are coming also in the same way. People know about this diffuse emission for 30 years. Everybody thought that it's very hot component of gas with temperature 10 TeV, but you know high dynamics. Potential well of our galaxy is 300 TeV or 100 TeV only. And gas, it's necessary to have gas with temperature 10 TeV. With 3,000 speeds it would go out. But it's a lot of this gas. Now we know that all this gas which radiates is in reality on these are stars which are radiating this emission. These are coronae and so on. This is a picture of integral, which integral got. And integral immediately giving you every point source with precision 1 arc minute. You are picking them up, and then this diffuse emission up to 100 TeV. And what we got, I will show you somewhere here. This is the spectrum. We found that this is the thermal emission with temperature of the order of 20 TeV, and this is exactly shock wave on the surface of neutron stars. These are intermediate polars, which are contributing and which are 10 million of white dwarfs are producing hot tail of this emission, and 10 power 8 coronally active stars are producing together completely different things. This is source counts, low mass X-ray binaries, CVs, and active binaries, coronally active. And this is their contribution to the luminosity. Extremely bright contribution from low mass X-ray binaries, CVs, and millions of stars. Now, boys have for 15 galaxies observed for Chandra, this ratio for all nearby galaxies, for Andromeda, for M32, for every galaxy we know what is the ratio of white dwarfs to neutron stars in that objects. Thank you. Excuse me, the kind of
I guess we now know it's very desirable to have X-ray vision. Questions? Oh.
With regard to the X-ray background, are you saying that we no longer have a consistent explanation for the X-ray background in terms of the combined spectra of AGN?
I can tell you that I believe that it's arrangements. My difficulty is the following. The situation is extremely good from 1 to 2 keV, for example, where people were claiming that the results 95% of background, now they're telling 8. From 5 to 6 keV today, when you're speaking with people, with some pressure, everybody is telling that he can give his hands if they know that it's 50%, up to 6 keV. Some are still speaking about 7. And these are people who are counting themselves. Second, we just corrected the total intensity of the background to 12%. Therefore, everything is going. Difference between Chandra and XML, for example, just in calibration of the background, is more than 20%. Life is not, it is not CMB. I am working in CMB, where we are looking for spectral distortion 10 power minus 7, and everybody is interested if you are proposing something on the level of 10 power minus 7. Here, 20% is okay. Main second problem is the following. We know the spectrum, and today this data from integral, we need to see component which has abrupt at higher energies, and we do not see until now enough such objects. And this question, maybe the main flux is coming from higher redshift, you understand this, but then there are energetical difficulties and so on. There are problems, not very big, but there are. But I believe that these are AGNs. Black holes are strong.
Mark.
Okay, this will be off. You're so slow. You're heavy weighted. Yes.
If I understood, you do not measure anything like the redshift of a positron line, so it is not formed very close to the black hole.
No. It's first we are measuring, it's coming from the distance of Dodo up to 6 degrees, so it is still bright. It's very far. Second, no any redshift, and we are rotating, therefore central part is not giving you Doppler. You are broadening, but you are not shifting due to the Doppler. Relativity corrections are very small. I told you that we are measuring center of the line with such precision that we can measure in reality motion of the electron around sun. Copernicus in your country will be very glad to hear this, but this was long ago. Okay.
Could you say a word about the last item on your list, please?
Oh, yes. I forgotten what was the last item, but we will return slowly, okay? Maybe. Okay. I think that last item in my list was a measurement of the spectrum of X-ray background. And there was also the X-ray reach, I only mentioned it. And with X-ray reach, I'm very proud because there are so many white dwarfs. And after Uhuru spacecraft, everybody was thinking that white dwarfs are negligible for X-ray astronomy. Practically, very small amount of objects and so on. They are big sources, but there are 10 million sources there. It's more than population of Sweden who are contributing to this thing. And they are rather bright. People saw them 30 years, and they were unable only to interpret that these are just simple white dwarfs. And mixture plus stars which are maybe 100 times brighter due to their coronal emission than our sun. And we see this.
In binaries?
Many of them are active binaries. These are the old results from Exosat and also results of Chandra. But not that results. We all saw the movie, how in Orion, many stars are rotating, all-time flares. These are young stars. I'm speaking about population of stars with age 2 billion years, 3 billion years, and they are active.
but still in binary.
Many of them are binaries.
Is there a mechanism for explaining them?
Oh,
when they're
people
not
are
binary?
saying because this is two stars with interacting magnetic field and so on.
But in a binary, I can understand. If they're not in a binary, what's the mechanism?
You know, we cannot prove today. We are speaking only about the objects which were detected by exosound. Maybe for 60% of them in Chandra, we know that they are binaries, spectroscopic binaries from optical light. For others, nobody knows. You know, it's question what is easier to find that they are in reality binaries or to find mechanism of the coronal activity for these stars. I don't know what will be. Okay.
Last question by you.
Roshan, you said that the root integral also discovered, in addition to AGMs, some X-ray, probably X-ray binaries with the very fast spectra.
Yes.
Do you think these are neutron star or black holes?
Some of them, I'm certain that there are two black holes, but it seems that majority are neutron stars. Because two of them are pulsing, which were studied afterwards. It's unbelievably difficult to study them. Integral has very low sensitivity, you know, in detecting them, but also to give good timing, it's not good. When you are pointing XMM, all radiation is out of the XMM band. There is no radio, how you can prove that it's X-ray pulsar. For two of them, brightest, it immediately came that they are X-ray pulsars.
Okay, I think we better move to the discussion.
Okay.
Although we have to be fed to be bright, I understand. But let's wait with the feeding for half an hour and have the discussion to wrap up today. Thank you. So we covered quite a broad range of subjects this afternoon. We basically started out with the sun and the chromosphere and hydrogen ionization, and then we had Christiana's talk about cloud formation and brown dwarfs and giant planets, and then Suzanne talked about starting winds from cool giants, and we had the X-rays to conclude it all. Are there any points that people want to bring up for discussion at this point? I had a question to your, actually, myself. I don't know where your it is. Yeah. So you actually calculate hydrogen atom, the level populations. Is this important for the ionization calculation, or is it just important for calculating what emission comes out?
Ionization, because the ionization mechanism is conditional excitation from the ground state to the N equals 2 state, and then photoionization is going to continue. So you actually have to have for more than at least 2 levels to get the ionization right.
Okay. Because the radiation, the photoionization, the radiation is too soft to ionize directly from the ground state. Okay. So one thing that came up in the break was that nobody seems to specify what kind of radiative transfer they're actually doing in terms of methods. So like short characteristics, long characteristics, flux limited diffusion, Monte Carlo, etc. So a few of the talks actually mentioned this, what is in there. I understand, so like in cobalt, it's what?
There are 2 modules for star and box and box and the star. And star and box with short characteristics, and the other is long characteristics. The basic assumption is the same, so as soon as LTE scattering is true absorption, the capacities come from a table. So if the table a grade, and it's grade radiation transport, and somebody provides a non-grade table, so then we get high frequency blends, so we get some frequency dependent, talking about line transport, talking again, instead of optically lines and continuum capacities.
So, but the choice between long and short characteristics is based upon what?
There's a sort of tradition with it. The auto module was box in the start, so there's the local setup and with periodic boundary conditions. And then rays are very convenient. They sort of leave at the left side and then come in from the right side, and that is treated by some index arithmetic. So that's very nice for integrating along rays. But if you try this with a box that's shut at the end, you get rays different lengths. It's just terrible. And then these supergiant models have sort of nasty opacities. They actually badly resolve, comparably badly. So they treat more temperature fluctuations and nastiness. So first attempts were just ran at some time and crashed in the radiation transport. And the short characteristics, they could get rid of some interpolation problems. I mean, they had other problems, but it was more locally. I mean, some things are better localized. So it's hot, and actually this one gets cool. And there's no crosstalk to the neighbors that much. So the other modules still have the problem. If you have a chromospheric shock, then shock is cool, but regions immediately next to it might also get some sort of cooling. So then typically it doesn't matter if the shock is a little bit broad, but the hydrodynamic, which sort of makes the shock and steepens it to something, it does not really know that the radiation transport later does not like very steep shocks. And it's actually, they separate these things, but actually it should be combined in some way. The short cell makes the speed that hydro can do it, it's part of the hydro operator. But the radiation, which has to deal with these varying capacities, and source function going with power effect, temperature, whatever the local source function is, that sort of suddenly sees those strong jumps, jumping up to the depth source function. And then it's sort of, if you interpolate, say, the source function very badly, then you have a cell, a hot cell and a cool cell next to it, but the cool cell gets a little bit from the hot cell source function, and it actually cools, and you get some sort of, you get this effect that the hot cell goes down, but you have some next to
So, but you're saying that the short characteristics it handles jumps in opacity source function better?
Yeah, but in my estimation,
Axel.
Isn't the difference really just that the short characteristic method introduces off-ray diffusion? So, so in some sense you're basically saying doing a certain type of error is actually an advantage here. It's not really that, naively one would have thought that short characteristics is a computational advantage in terms of polarization. And I don't think that's the case. Do you agree with that? It's not an advantage if you want to have an efficient polarization method. Then short characteristics is not really
depends on
any different.
Cobalt, the polarization is done with OpenMP, so we need shared memory, and both radiation modules.
Yeah, but if you're talking about domain decomposition, no advantage. Or otherwise,
it's very similar. That was not the reason, and
yes.
Both they have with it, we don't have MPI, so that might be another issue.
But maybe with other coordinate systems there's an advantage. If you want to go to spherical coordinates or something, then of course short characteristics has advantages.
Is that the remark? I guess.
Let's finish this particular part first. I have a related question for you.
Okay, then Paul.
If you want to propagate long characteristics in an AMR grid, then you have a problem in that your refinement, if you don't want, the advantage of AMR requires that that you have isolated regions of refinement. But in the presence of long characteristics, you need to worry about the shadows of highly refined regions, and you're stuck with the refinement. Whereas short characteristics perhaps don't have that disadvantage.
Okay, then.
Well, I should think that many of these technical questions could be resolved by comparison if we had good analytic solutions, right? Where typically we do not. And therefore I have a question for Ed. From your experience, would you have a recommendation for either a specific or a general type of test problem that we could use in order to compare these things?
May I elaborate on the whole question then?
I'm not the chair.
I know, but it's your question. What I'd like to say then is, first of all, we're doing approximations of one kind of matter. And since the intensity of the radiation field is not a Lorentz scalar, the frame in which you make the approximation gives you different results depending on the choice of frame. And the point is that there's certain, you must think of the photon gas as a fluid. Just as the material has its own frame of reference, so does the gas of photons. In use in relativity, there are two standard frames of reference, one known as the Landau-Lifshitz frame and the other the Eckhart frame. But other frames are possible. What I recommend, and in fact I can, for example, in certain cases have shown, that if you choose a frame, a local velocity frame, and do your approximations, then that gives you an Eddington factor. You actually, the frame in which you make the Eddington approximation, the traditional Eddington approximation, in which you say in this frame the radiation is approximately isotropic, that gives you an Eddington factor. There's the Eddington factor turns out not to be a funny thing made up for calculation. It is a physically determined quantity. So that's the first recommendation. First decide the frame you're in. Now, of course, most of the analytic studies are done in the matter frame. So, for example, we have an exact solution for radiation up through a half space because we have the Wiener-Hopf technique gives you an exact solution. So that's an easy one. There are probably certain simple ones. I mean, in for example, the cosmological simple Robertson-Walker, you should do that and see what the aberration does and all that. Those are the two simplest ones. But there are also probably cases where you can do pretty exact solutions numerically. And also the method of Chandrasekhar can give you asymptotically quite exact solutions. So those can be worked out. But the standard atmosphere solution of Wiener-Hopf is a good starting point. In fact, people, Axel and I were looking at last year about testing a program, and just even giving the static case, by the way, that's an analytic solution.
Yes.
We had, you have a standard compressible atmosphere, and with elementary transfer theory, you could get an exact solution, which the bottom was polytropic, and it goes to an isothermal thing. As in the Earth's atmosphere, the original stratosphere was discovered as an isothermal layer 1899. So there are a few things, but for me the main event is to do whatever you're doing in a well-prescribed frame that's dictated by physical considerations, such as Eckhart and Landau-Lifshitz. So I don't know if that's much of an answer.
Well, I have sort of a follow-up question, if I may. I mean, one of the things that I was thinking of when thinking about possible analytic backgrounds, right, is to make up a more or less Mickey Mouse type atmosphere where all scalings are powerballs. The reason for this being that there is no intrinsic length scale. And then one might conceivably, I mean, it need not be a static atmosphere or gravity or whatever.
You can work backwards and decide what solution you want and find what the right situation is and then stick it into your program.
Yeah,
that can be done. Sure.
Ed's solution, of course, goes through tau equals 1.
Mm-hmm.
And that's therefore of interest. And furthermore, it actually includes radiation pressure.
Yes.
So there's radiation pressure in the hydrostatic equilibrium.
Mm-hmm.
So it's a non-trivial solution, but it's one-dimensional. And you are maybe interested in two-dimensional or multi-dimensional solutions.
Well, one thing we're thinking of, if you have
The
this...
radiation is not one-dimensional.
Yeah.
Okay.
Thermodynamic scalar.
Yeah, right.
Correct, yes.
Okay, that's true.
We have more methods, of course. Flux-limited diffusion. Who wants to talk in favor of flux-limited diffusion then?
Who is using flux-limited diffusion?
Well, I would like to say a word about that if someone else...
I don't see. So nobody here uses flux-limited diffusion? Is that the conclusion, or are you afraid to say so?
I'll show you the flux-limited diffusion calculations for accretionist tomorrow.
Tomorrow. Okay.
Maybe wait.
No, I'm not going to defend it.
No.
Well, I can say a word.
Yes.
It's just that if you do expansion, say in mean free path or something like that, you get a series. The standard method is to make rational approximations. The sort of thing you might, if you got 1 minus x as your solution, you would replace it by 1 over 1 plus x. So these rational approximations are just what the flux-limited diffusion is. For example, if you look at radiative cooling processes, which gives you an integral for the cooling problem, you expand that, your leading term is Laplacian, your next term is Laplacian squared, you can write that as Laplacian over 1 plus Laplacian. It's just a simple rational approximation, and that's what this is in effect. A rational approximation. So that's why it's good at both ends and so on. So that's a perfectly good thing, but there's a well-defined method, and you can get higher order representations. You can make more complicated rational functions and gain accuracy. There's a whole culture there. Look in Van Dijk's book on fluid dynamics for a start.
One question would, of course, be, is the flux-limited diffusion approximation any faster? If it's computationally of the same expense, then it wouldn't really make much of a difference.
It's good with spectral methods.
I mean, the reason why it's, of course, not necessarily fast is because you have to solve it implicitly in the optically thin regime. You all agree? So what is then the advantage of the flux-limited diffusion approximation if it's not even better? I mean, computationally better.
It's like Monte Carlo, it's bloody easy to program.
So implicit, that's not so bloody easy.
Oh.
But that's because you have no time derivative. See, then it's a diagnostic instead of predictive equation.
But the flux-limited diffusion approximation has a time derivative.
It depends what you do. If you just... Most people use without a time derivative.
But in any case, it's either implicit, I mean, it's parabolic. Yeah, it's parabolic, that's not
So it's good pretty good with spectral methods.
Yeah, sure. But nobody's using that with spectral methods, of course.
Right. Yeah.
But you mentioned Monte Carlo.
Yeah, I was just thinking. So it's actually Monte Carlo radiative transport is very popular to do purely radiative transport. There are some instances where people also combine this with hydrodynamics. I'm not sure if there's anybody here who does that. The question you may ask is whether this is more a matter of convenience that they already had this radiative transport code and put it into. I know one case, I guess, where this happened. Peter.
Well, yeah, there was one case in practice that was Peter Wojtke was working on this in the lighting group for a while, and he was doing two-dimensional models of post-AGV star with dust formation, etc., using Monte Carlo radiative transfer. That worked just dandy, but the instabilities he found made it necessary to go to 3D, and for that there's totally no way that you can get any reasonable approximation using Monte Carlo. The reason for this basically being that in his models it turned out that the little caps, as it were, of dust that form as it were a blanket, a little small, more like a pillow than a blanket, as it were, between the dust and the star. And the additional heating that is trapped in there made a lot of difference to the dynamics. If you will properly resolve that, then you cannot. You must have so many rays that you couldn't possibly do it with Monte Carlo. But that's a practical limitation, you know. I mean, it's as I said, it's a fairly trivial thing to program. So I think that's why it's popular. In fact, one sees that many people sort of try to reinvent that particular wheel. So.
And the problem is with the best that it was very difficult to come from optical sync to optical signaling.
Exactly.
So this was actually a tricky part, and we know the solution for the optical sync part, and Kelly know the solution for the optical sync part. But we need to make the transition physically meaningful and then get to all the best parts. And that's actually the painful part.
Yes.
But it is always the painful part, right?
Yes.
What are then the advantages, the particular advantages of the Monte Carlo method?
You can parallelize very easily.
So it's also very flexible. We had a conference on radiative transfer in Heidelberg some years ago, and there are people from, let's say, nuclear physics or so, and whenever you have a high-dimensional problem, usually they go to Monte Carlo methods because they don't care about the geometry. So I would recommend it for cases where you have very complex structures.
Are there any sort of predictor corrector type things in this field? I'm just generally asking. I mean, one thing one could do is use a method that is, as we say, is easy to implement under many circumstances. Give you an idea where the real nasty points are, but just like what Cristiano was saying, and then use another method to zoom in on those. Is that a possible strategy?
Yeah, I mean, there are methods for ray tracing, because if you integrate along the ray, then of course you can watch what the source function, for example, is doing. And then, for example, if you hit the diffusion limit, that's what we did, tell the ray tracer so, and then he can do big steps until this region is crossed, while other ray tracers would do very tiny steps, because they think, okay, it's optically thin, that's it, then we have to do little steps. But that's for the ray tracing.
Okay.
Any other issues that people would like to raise in the discussion? I don't know. Oh, Axel.
I mean, about the chemistry, is there actually any crosstalk between people who do chemistry in astrophysics and those who do chemistry in the car industry, for example, or motor industry or something? I mean, in industrial fluid dynamics, there is?
We have in Germany a huge kind of special research area where there is a research is funded with a lot of money, where they have mathematicians, engineers, and astrophysics, and we got a lot to learn from them about the numerical treatments of these chemically propagating fronts. And this was actually one of the questions I wanted to ask Sven, because what they are doing is they are tracing the chemically propagating front to the unburned medium, so to say, to the unprocessed medium. And this gives them very precise results, because what they are interested in is to make the engines as small, as efficient as they could, right? And the whole question is how to model the most detailed these burning fronts, so that they know how much fuel they need. And in some sense, I also would think that it's very important for acid zero context. And it has been applied in supernovae simulations, actually. They have taken exactly the same method, have worked it into their hydrocodes, and are able to predict now much better the nucleation, supernova nucleation processes than before. But it's, there is a knowledge.
I always understood that the fact that we understand carbon stars much better than oxygen-rich AGB stars is precisely because the formation of carbon dust was extensively studied in stars by car manufacturers. But I'm not sure. Maybe this is a legend. Do you know?
It's not quite a legend. We got many of the data from
Rashid.
Yes.
I understood that there is taboo from Omar to discuss accretion disks.
Well,
But unfortunately, I'm in committee and I cannot be here tomorrow. Therefore, I decided to ask question about not about the accretion disk, but about the spreading layer on the surface of neutron star. And on the surface of neutron star, we have the atmosphere, which is supported with huge flux, locally Eddington flux. Luminosity local flux is exactly Eddington. Okay, I'm coming, because I'm speaking especially for you. Oh, sorry. Yes. On the surface of neutron star, we have the spreading layer after the boundary layer. And this spreading layer is fully supported by radiation pressure. And my question is the following. It's not extremely optically thick. Optical depth for Thomson scattering is 10, 15, 30, 100. But let's consider the case of 10. And in the case of 10, where we should finish the consideration that there is inside radiative pressure. Because I can describe the same atmosphere. There is flux, everything is supported by radiation pressure, by radiation pressure force, not by the pressure, but the radiation force. But I can also write the diffusion equation and answer will be absolutely the same. Now when I return to the optical depth of Zodo 1 or 2, situation is becoming much more shaky. It's not good to describe already because radiation is not isotropic. There is no, what usually people, where is the boundary where we can consider that there is radiation pressure and where we are absolutely free and this only force.
But the thing he mentioned, referred to
Yes.
that we had talked about, is that if it's plane parallel, there are analytic solutions all the way.
Yes, because you can work with the radiative force.
But the radiative force.
Yes.
But then it gets optically thin.
Yes.
And that turns into an isothermal atmosphere held up by the gas pressure.
It is not, the temperature might be very low. It is very difficult to speak that.
It goes into equilibrium, unless it's a wind. Are you talking about, if it's an atmosphere, I'm allowed to be plane parallel?
Yes, it's plane parallel.
Then I think you could write down a simple, is it gray? Gray or with a funny
No,
spectrum?
it is gray.
Then I think there's simple solutions which may involve matched asymptotic expansions, but pretty standard simple solutions. If I may send you one, if I
will be glad. I am getting these solutions myself, therefore I will be glad to see analytical solution which may exist.
Okay, you have his email in the list.
Yes.
But otherwise,
and there is no any transition around.
Well, yeah, there's a boundary layer. There's a transition layer, but there are two regimes and they match up nicely.
But again, not to speaking about the...
If you don't mind inverse hyperbolic tangents, it's pretty easy.
Yes, but I have again the turbulence and I...
Turbulence?
Yes. And then I need again in the same layer what will be the friction and so on, because I am describing this as, you understand me, what people are doing, where they are stopping to consider that this is that there is radiative sound, the radiation dominated plasma sound.
But if you're saying there's turbulence, then I've had it. I mean, I can do this too, but turbulence we're finished, you know?
Okay.
But no, this is just radiation forces, hydrostatic atmosphere. But if you want to put in turbulence, then we have to talk at length.
No, but stratosphere also is not static. Everybody knows this. There
I
are
know.
beams, there is turbulence.
I'm not saying it's realistic. He asked me if there's analytic. But for turbulence, I can't do anything.
But I was speaking especially with people who are doing the stratosphere.
Oh, yes.
And they're telling that there are stochastic motions, and if you average them, they're going according to Kolmogorov law.
Well, everybody gets Kolmogorov law. Zakhar gets it for weak turbulence, etc. It's a miracle. But up there, it's rarefied gas dynamics, and the normal fluid equations don't apply. They're more general fluid equations. And that's a long story that I would like to talk to you about.
Okay. Then Axel has a last point to bring up.
I mean, at some point, I think, and maybe that's a topic for tomorrow, rather, the issue, it came up already, I forget who it was, somebody presented a comparison between doing the scattering as a scattering opacity as opposed to an absorption opacity. And there were certain differences in the optically thin regime, but on the other hand, that was just a one-dimensional test. So what is the conclusion so far? That we may be pretty alright in the optically thick case, but in the optically thin case we can be vastly off, or are there perhaps more other caveats in 3 dimensions even that have not been assessed?
You're talking about solar atmosphere or stellar?
Or even, I mean, anything. Also, does electron scattering dominated accretion disks? That could be just about anything. Well, it's very important, of course, and routinely neglected.
I mean, we did a 2D benchmark in continuum where we had an accretion disk with a Titori disk, so to say, around a solar pad star, which was a bit younger. And it took us like 3 or 4 years to bring together 5 European state-of-the-art radiative transfer codes. And it was the longest project I've ever been involved in. Very hard work because we were diverging in many aspects. But finally, we published it as one benchmark. And still it had errors of 20% or so. So that's there. And it is scattering by illumination of an atmosphere from the side. So that's a tricky configuration. That's all I know of.
But then you searched for scattering properly, with iterations.
Yeah, the scattering was in.
And you needed many iterations.
The codes did it differently. We had like 3 Monte Carlo and 2 ray tracing codes.
Is Monte Carlo an advantage in terms of scattering?
It is very hard to know what is the advantage if you don't know the real solution. That's the problem. I mean, it seemed like the Monte Carlo codes were converging and the ray tracing codes were converging. But
they were converging to different solutions?
Yeah. So I will report on this tomorrow morning.
All right. Okay. So then that's maybe an appropriate point to stop and look forward to tomorrow morning. We start actually at 9 o'clock with Jürgen. And now there should be some drinks. I don't know where.
Yes, should be just outside, so if you just bear with us.